So as stated here, the FMEA could be kind of qualitative or quantitative or something in between. What does this mean is that either it includes, for example, quantitative data. So you can, for example, have field reliability data included in the FMEA, and then you can have test data, qualitative data, and then you can quantitative data, and you can compare those and utilize those in the FMEA. Quite often it's mainly qualitative, so it's more brainstorming the potential problems and then trying to figure out. You can include simulation data, whatever data is basically possible to include in FMEA, because it's more like an approach rather than like a direct recipe how you do something. So the nice thing with FMEA is that if it's well documented, then it's also, you can use it as a diary or documentation of the, let's say, design changes, process changes, material changes. So later on, then you can always come back and see, okay, now we did, because of these reasons, we changed this and that, and then it helped or made our life worse, whatever is the consequence, and then you can come back and see that, okay, you can utilize it as a way of collecting data. So the big picture anyway is the identify potential problems as early as possible. So as I have already mentioned, reliability engineers quite often are pessimists. So we think that, okay, what can go wrong first, and then we think that, okay, how we can minimize the probability of this problem will occur. So this is kind of a quite simple example of how the rationalization process goes on. So first we need to think that what is the failure mode, and now you remember our definitions. So failure mode is something which the user notices, and it's what this failure mechanism has caused. So for example, you in the morning you put your mobile phone to have an alarm, and then you miss the lecture because the alarm fails. So that's the failure mode, and the effect is, I mean, that the alarm fails, that's the failure mode, and the effect is then that you miss the lecture because you missed the alarm or you missed the call or whatever. And the cause behind is the failure mechanism. And that is kind of the let's say, engineering problem, the physical problem which the device had. And now in this example, it is related to the loudspeaker. For example, of course, it could be something else, but it could be that you miss the alarm because the sound of the loudspeaker is too weak or it does not exist at all. And the basic reason behind the too weak sound could be, for example, contamination. So here is just a picture of this kind of a loudspeaker, miniaturized loudspeaker, which could be in your phone. And as both microphone and loudspeaker, they are, the physical basis is a moving membrane which moves the air. So it means that this kind of a component cannot be completely sealed. So it cannot be hermetic in that sense. So you need to allow the external air to move in and out from the component in order to get the sound waves in and out. So in loudspeaker case, of course, out, in microphone case, in. And that is typically done so that you have a hole there somewhere. It's quite often underneath the component, like here. So the sound waves now, when the clock should start to ring, there's a membrane inside which starts to vibrate the air, and then the sound should come out from here. If this hole here is blocked because of contamination, then the sound is weaker, and then you might miss it. So then, in order to prevent this, you should do some actions. and these are now so-called recommended actions. So what is the way how you decrease the probability of this kind of a failure? So if it's a mechanical failure, like some interconnection has failed, then of course you pay attention to that one. But now if we think that the contamination was the problem, so this hole was blocked, or even more severe, some contamination had entered inside the component and accumulated on the membrane itself, then you should do something for that. Okay. Yeah, RPN. I'm coming back to that one in a second. So RPN is risk priority number, and that is the critical thing which we are kind of using in FMEA to let's say categorize the problems. And there's a certain way to calculate it, very simple way, and I'm coming back to that one in let's say 5 minutes or something like that. Okay, and then so basically what one can do, you can let's say improve the sealing of your phone if the contamination is coming from the use environment, for example, or you can maybe do something here locally to prevent that. Let's say if it's dust which has accumulated here, then to prevent or slow down. Completely you cannot prevent it because you need to allow the movement of the air, but something you can do in the design, for example, is to prevent this problem. Okay, this was just a hypothetical problem, but this is the point was just to show that how the reasoning is done in FMEA. So now I would like to go through the kind of as an example the process, which steps in typical FMEA contains, and this is also the same thing which you then need to do in your assignment. So first of all, you start with the actual product, whatever is the product, and so you could, for example, start from the blueprint, the engineering drawing of the product. Or if we would now make our FMEA on this kind of a steam operated tractor, then we could start with the engineering drawing, the blueprint of that. So we could basically here start picking up all the parts, individual parts, and start thinking that, okay, in the let's say steering system, what are the critical things? All these mechanical parts, are they critical? Let's say if you lose steering of this kind of a product which weighs, let's say, 2 tons or something like that, of course it can cause safety issues either to you or to somebody else if you cannot steer it properly. Or you can think that, okay, what happens, how it is made sure that if you lose your steering and it goes to the, let's say, some deep hole, it's not flipping over. So where is the center of the gravity, and can you, for example, build something which protects the driver if it's flipping over, and these kind of things. So again, tearing the product into parts and thinking from every part, what can fail, how these can fail, and what is the consequence. So now in FMEA, the consequence is kind of the key thing, and that is the RPN. One of out of 3 parts of that is the consequence, the severity of the problem. So if this was an ancient example, maybe this is a future example. So you could also do the FMEA on Star Trek USS Enterprise, and then of course you need to also have the blueprint of that. So because this is just nice blue colors, that's the reason I took the example. So basically also here, of course, it's not very detailed blueprint, or I don't know, but I would assume that there would be all these could be also divided into a million other pieces, but still you can basically see the all parts which the USS Enterprise is composed of. So you could start thinking about for example, the landing bay. What kind of things are related to the landing bay, and what structures it have, what kind of things can go wrong when it lands somewhere on uneven terrain or whatever. So this is just the idea. If you have the engineering drawing, then that's the best way to start. The other thing is that you could also start from the product itself. So this is a classical Finnish downhill sledge. So you could think that, okay, how could this product fail? You can again start with different parts, like again the steering, this bolt which connects the steering wheel to the front sledge. So this could, for example, be a very critical part from the safety. So because if you again lose the steering, then you are in problems. You have the brakes. This part is mechanical part, so maybe quite robust, but also there is the attachment. So you push with your foot, this one, in order to brake. And if that fails, then of course you lose control of the speed, and that could also be quite harmful. On the other hand, you have here the seat, which maybe the reliability may be not that high. It's not mechanically very robust, and depending how you store it, if you have this one the whole year into the sunlight, so UV radiation really quite fast, maybe within a few years, will start to decompose the organic, the polymer material which is here. But on the other hand, the failure of the seat is not that severe. Maybe it's a little bit annoying. You start feeling the bumps more easily when it, for example, hardens or something like that. But from the severity point of view, the failure of this part is definitely not that critical if we compare it to this part or that part or that part. So that is just the idea that start from the product, rip it into parts, think every part how they can fail, and then think what is the effect of the failure. And as I said, there's a possibility also that you are not using FMEA on the, let's say, product or device. You can also use FMEA on the process itself. So this is also quite typical in the processing industry. So you can use the same approach, thinking about that how a certain, let's say, for example, electronic component is manufactured, and then you split the process into parts, and you start thinking every individual processing step, how it can cause a problem, which you would then see in the actual component to be manufactured. So this example here is coming from the so-called wafer level chip scale package, which means that this is even stacked component, so would be quite advanced package. Could be, for example, let's say the main component of your phone. So having the actual IC processor chip, the logic, together with stacked memory chip, and this would be then assembled into your phone. And now if we think about the manufacturing process, so as I said, this is wafer level process, meaning that up to here, basically the wafer, it is handled in wafer level. So the processing is happening in wafer level. So we have first the fab process, wafer level process, so meaning that this is so-called front end of line. So the actual transistors are manufactured into the silicon wafer, then we have two silicon wires, back end of line, meaning the metallizations, then you have the solder pumping, and so on. And then you kind of continue assembling the whole product. And now if we think that something goes wrong here, let's say contamination in the front end of line process, then you may see it. You don't see it after here. If you have some testing, you may not see it even after here. You may not see it after here. But then after you have assembled the whole package, and then you see that, okay, the processor is not having proper communication to the memory component, is because there was certain parts, there was some contamination, process contamination, and certain part of that chip is not working properly, or something like this. So the point here was just to highlight that as well you can use the basic idea of FMEA to a process rather than a product. I would assume that all of you will do your assignment on a product, but of course it's possible also to do this one with a process if you really, let's say you are working part-time in some company who is doing some processing, then it's of course allowed to use that as an example. Or but most probably this is not that valid for our first assignment point of view. Okay, so that was step one. The first step is to review the product or process, so to see what parts it is composed of. And then when you have all the bits and pieces on the table, then you start thinking that, okay, how this can fail and what causes the failure. So basically you can consider the root cause, or the who is or which is causing the failure from different viewpoints. And here I have listed few. So people here mean the user or the manufacturer or some human being who is affecting on either on the manufacturing of that product or who is using that product. So let's say, for example, the first example where we discussed about the failing of the alarm of your mobile phone, then one could kind of consider it that how the manufacturer, so was the contamination originally coming from the handling during the manufacturing. So somebody had put their thumb on top of that hole and already put there some grease and maybe some ionic contamination, which then let's say migrates during the usage to the actual membrane and start causing problems. Resonance frequency is changed because of the mass is changed or something like that. Or is it that you as a user who is causing the contamination? So by having your phone in let's say environmental conditions where it's not kind of designed for. Cannot kind of now recall, maybe you are doing something like wood machining or something like that, where there's a huge amount of dust in the air, and then the dust kind of enters in all the parts and then blocks the membrane or blocks the hole or something like that. Okay, this was a little bit arbitrary. Then concerning the failure from the method side, so this is meaning, for example, testing methods, design methods, whatever methods. So what you are using to manufacture the component. It's quite close to the next one, which is the equipment. So there's basically not that big difference. You can kind of merge these together. So equipment is typically more related to actual manufacturing equipment. So what kind of tool you are using to mount the component into the motherboard, or what kind of equipment you are using to inspect the actual connections or the sealing or whatever. Then materials, that's just the how this, from which materials this component was manufactured of, what is the basic selection of materials, and so on. And then you have the environment. So this is either the production environment, it could be the transport or storage environment, or it could be, as most commonly it is, the use environment. So that again could be, for example, directly related to the people, so the user, so in which kind of conditions the user is using this in specific product. And then while thinking about certain component and certain failure mechanism, then you typically end up for failure mode. So if it fails, it can cause this kind of a problem and that kind of a problem, and these are because these things are very interlinked. And then you end up having, let's say you have only 10 pieces on the table, so 10 components. Every component you consider different failure mechanisms and modes from these different viewpoints. So quite rapidly you can end up, for example, 100 different failure mechanisms and let's say 50 different failure modes. Then the good thing or what would be beneficial is you start grouping this somehow. So you, for example, first pick all the failures which are somehow user generated, because then you might have different solution for those problems than, for example, the electrical problems. Electrical problems maybe you need to solve in the design table, but user generated problems you may at least decrease the amount of those by rewriting your instruction manual to clearly state that, okay, don't put the gas on the microwave oven or something like that. So that could be one option of limiting, for example, the use environment. You state in the manual that, okay, you can use this product only at these temperatures and you cannot expose it to high humidity or whatever. So you group them according to different categories so that you can have kind of a combination of failure modes, because quite often then with a single improvement you can affect on several different failure modes or mechanisms. So meaning that with one hit you can get more fly. So your corrective action has more effect if it affects on several different potential failures rather than only solving the problems one by one. Okay, so that was the step 2, and now you should have basically all the parts and all the possible failures related to those parts, and also you should know what is causing the failure, so where the failure is originating. And then you start to thinking that, okay, if this problem occurs, what is the effect? What is the consequence? So here, if the failure occurs, then what is the consequence? And you think it from the severity point of view. So now I already want to emphasize that these numbers, it is in your assignment, it's extremely difficult to define. You just need to be consistent, thinking that, okay, this problem is more severe than the other, and for the previous one I gave 4, so now I need to give 5 or 6 because it is a little bit more severe. The absolute numbers are not important. It really does not have any effect on how many points you will get in your assignment, what numbers you pick. Just be kind of rational, logical with this. So the extremes are typically quite easy to pick. So for example, severity number 10 means that the failure is something that could really kill or very seriously injure the person who is using or who is working with that product or whatever. So this is severity rating number 10, and severity rating number 1 is that the severity is practically 0, so the customer won't even notice if that failure occurs. So it is something that could be, for example, some internal visual thing which you don't even notice. Or number 2 could be that just because of the sunlight, the actual color of the product slowly changes from shiny bright to a little bit more mattish, and that is something that really does not affect on the usage or usefulness or use of the product itself. It's just a cosmetic change. Then of course the severity is very low. Quite often the difficulty is to make the difference between 5 and 6 or something like that when you are here. So what is the difference between high degree of satisfaction and normal degree of dissatisfaction? So if you are really annoyed or just annoyed about the problem. So that may be also a personal question or opinion. So here is just to help you in picking up then these points. Then I have added here another table which is basically quite the same, but maybe a little bit different wording. So but the scaling is the same. It's always in the FMEA. The scaling is the same. So from 1 to 10. So now for each and every failure mechanism or failure mode, now this is you can do it basically both ways. Maybe it's typically you have a little bit less failure modes than mechanisms. Then you can affect the rating for failure modes, and then you think how you can improve the mechanisms. I mean, affect on the mechanism so that the mode is less frequent or less severe. This is a little bit, let's say, how you pick your words. So sorry if I'm a little bit confusing about the modes and mechanisms, but basically it does not matter if whether you use modes or mechanisms, as long as you kind of yourself you know what you are talking about. Okay, so now we have for, let's say, for every failure mode we have one number, which is the severity. So you had 10 parts, 50 failure modes, and 100 failure mechanisms, and now for each 50 failure mode you have the same severity ranking or rating, so that how severe is that mode. Then next you go to the second number, which is the occurrence. So how often this failure could happen. So again, number from 1 to 10, and the number 1 is that basically this specific mode is extremely rare. For example, 1 occurrence in more than 5 years, or 2 occurrences in 1 billion events. So if you, for example, use that, or there's 1 billion products on the market, then 2 of those will have this failure mode. There's also this, if you are using the FMEA on the process, then you can use these process capability indices, which are kind of statistical values from your process. You can use those. So then you can really do this quantitatively. Let's see how this now turns out if I click my, okay, maybe at least not with the, remove the pointer. Let's see what happens. This should lead into the Wikipedia where these are defined. And now I really don't know if you are seeing my browser.
We are seeing the PowerPoint.
Yeah, you are still seeing PowerPoint. Okay, sorry about that. Then I will just stop this one. But basically, if you go to the Wikipedia and put their CPK, process capability index, then you will find out these what these numbers mean. So basically, it's the mean of your product, and then the deviation. So, for example, 6 or 3 sigma deviation, you need to define the specification limits, upper and lower, and then you how well controlled your process is for certain parameter, and then you can get these values. I hope that you will now see again, or you still see the slides. Yes. So now we jump to the next slide, which is the basically the same, just a little bit different numbers. So I mean, not different, same numbers, but different explanations, maybe a little bit more simplified. So the failure occurrence is very high if it happens, let's say, in 50% of the time. When you use it, every second time this problem appears, then you need to rank it to 10. If it's 1 event out of 3 use events, 1 failure out of 3 use events, then it's 9, and so on. And if it's 1 event out of 1.5 million use cases, so 0.66 parts per million, then it's very unlikely, and you assign the 1. So again, I want to emphasize that this is something, of course, you don't know when you're doing. Typically, you don't know if now in this course when you're doing the assignment. So just pick a number and be consistent. Try to think that, okay, now with the previous mode I gave 4 because I think it's something like maybe once a year it happens, and the other one is definitely much more probable, so let's put 7 because yeah, it happens once a week or whatever. So now we have 2. We have the severity rating and we have the occurrence rating. And now we have the still one more, which is let's say maybe even more difficult to assign now in this our assignment case, because it's the detection rating. And now you can consider this detection also from 2 different viewpoints. First of all, the detection means that how easy it is to detect the potential problem beforehand. And now you can consider this with 2 different ways. You can consider it from the manufacturer viewpoint. So is there some inspection or testing method which could see the potential failure mechanism, the problem behind? So for example, you do some electrical measurements after the product has been manufactured. So there's a question. So if you don't have the exact numbers, likelihood or so, it's quantitative FMEA, and if you do qualitative or okay. So maybe I was a little bit confusing here. So basically, if you have, for example, the process capability data, so you are now doing the FMEA from a process, then you can really calculate something. You can calculate the CPK values. Then definitely this is quantitative FMEA. But you can also consider it, let's say, from qualitative point of view. Like here, even we are assigning the numbers. So in that sense, we have numbers, but still they are not, let's say, quantitative numbers because we don't have any actual engineering way to measure them or define them. So for example, you could have, for example, from occurrence. Let's go still back. This was a very good point, and it's good that you asked, that we are talking about the same language. So for example, this one, we are thinking about the occurrence. If you would be now in a company who is manufacturing something, So basically, it is possible to get this out of your field data. You can, for example, have, let's say, the stupid example again, but let's come back to the mobile phones. So when a customer has a problem with the mobile phone, he or she takes it back to the shop and it goes to the repair. And then in the repair center, they are not doing very detailed analysis, I mean, on the actual failure mechanism, but they are at least marking the failure mode. So, okay, this product during the warranty time was brought back because of the battery had died too early, and then they changed the battery. So you will get a data, actual qualitative data on how many battery returns you had during the warranty period for, let's say, 2 years. And then you have really a quantitative FMEA. But then if you just need to consider that, okay, battery failures may be quite typical, and they are maybe the within the 5 most typical problems which our product faces, then you think that, okay, it's quite high probability, so let's assign 7. That's even you give the number 7, but it's a, let's say, qualitative 7. It's not quantitative 7 because it's not based on actual hard data. So this is at least how I think it. I hope that this little bit clarifies the idea. Okay, good. Okay, so now we were in the detection rating, or was there? Are there controls supposed to exist higher, or should we consider that there is a theoretical way to do a test? It counts as in real life. So in real life, theoretical way to do a test. No, it means that if you consider that one from the manufacturer point of view, let's say that again you are manufacturing a product and then you do some testing. So now the detection rating is based on how well you think that this testing can find the problem. Meaning that if the problem is something that the tests what you are doing, let's say that you are, it's a little bit difficult because we have not yet went into the, but burn-in testing, for example, is when you have the product ready, then you kind of put it on. You can put it on so that it has the, let's say, normal operating conditions, or you can put it on in, let's say, harder conditions, higher stresses than it's the normal, like put it on in a furnace. And then you do some kind of, let's say, testing of the product. And now you think that would this test find 100% out of those failures which could cause the problem, then you assign 1. If it's a failure which you would never find in this test, then you assign 10. And if there's a high probability that you will find this, let's say, defect during the testing, then you are somewhere here. And on the other hand, you can use it from the user point of view. So does the user get any early warnings that now this problem might happen? Let's say you are driving your car, you are before the tire explodes, you get an early warning if you check your tires frequently. So you start seeing that, okay, now my tires are wearing off. They have these micro cracks at the side because the rubber is getting old. So then the explosion of the tire is not something that it's completely unexpectable. But there could be some other problem in the tire, some manufacturing defect, which you cannot see. There's a air bubble or the now I don't know the English words, but the tires, car tires, they have these steel wires, which is hardening the rubber in the sides. So if you hit some hard object, then they protect the tire to be broken. So if, for example, those steel wires would be, let's say, there would be some defect, they would be partly missing, or they would be, let's say, because of some poor process control, they would be not organized or arranged in a symmetrical way, but there would be a kind of a hole or missing some of those. Then of course that is something that you as a user can never see because it's not visible. You don't have the tools. And then if the tire is exploding on that specific location where there was this kind of a hidden defect, then you need to assign it 10 because there's no way for you to see it. But on the other hand, the manufacturer would have seen it if they have used, for example, X-ray to check that, okay, how these steel wires, how they are they as expected. Okay, so hopefully that clarified. And really, once more, this is difficult. This will be extremely difficult for you to really pick what number you have, but just do it in a consistent way. That's my kind of advice. Be consistent, and then that's okay. Because even in a few slides, I will have few, let's say, basic rules of thumb, but they are always dependent on how you pick these numbers. So there's no an absolute critical threshold or something like that, which is a good RPN and which is bad RPN. Okay, so we have again two different tables. So having just few different viewpoints. So now you have assigned for all failure modes severity number, detection number, and then okay, now I already the severity, occurrence, detection. Sorry, losing my words. So you have assigned three numbers. Each of them are something between 1 and 10, and then you just sum up. So you calculate the risk priority number. Sorry, no, you don't sum up. You multiply those with each other first. So you get a number which is between 1 and 1,000 for each, and every failure mechanism, and then you sum up the RPNs to get the total value. So let's say if you have now a failure which is you have given severity 1, occurrence 2, and detection 1, then it's 1 times 2 times 1, which is 2. It's extremely low, and then you have the 50 out of those, and then you just sum up them, and then you get the total RPN number. The absolute value is in that sense meaningless because it's dependent on how many modes and mechanisms you pick. But that the total number, RPN number, is used to evaluate what is the actual effect of your corrective actions, your improvement. So how much you were able to improve the product or decrease the effects of failures by doing the improvements. So as I said, the actual number for individual mode is not important in that sense that we cannot, it's dependent on how you assign the values, but there are certain rules of thumb, and this could be one way of thinking, that if the RPN for certain failure mode is less than 18, then you can disregard it. It's a minor risk, forget it. If it's more than 64, so what is that? If you have 4 times 4, it's 16 times 4, so it's 40 and 56. So it's on average quite close to 4. Then if you exceed this value, then it's kind of a major risk. So typically you need to do something. If it's in between, then it's up to you to decide, okay, is this risk which we can take, or is this something that we can and need to do? And it's of course dependent also how easy the corrective action could be, how time consuming, how costly it could be. So you can even pick that, okay, maybe we'll improve this specific mode because it's much easier for us rather than the other, even the other has slightly higher RPN number. So here's another table which basically kind of just describes the extremes. So if you have everything, occurrence, severity, and detection, they are all one, of course. There's no actions needed. That's the ideal situation. The problem never happens. If it happens, it does not cause any problem. The customer even does not notice it, and it's very easy to see. It's easy to detect or see beforehand. On the other hand, of course, we have trouble if everything is 10, and there are descriptions of these. So, for example, even we would have 10. So occurrence is 10. So it's very frequent. It is easily detectable. The severity is small, but still maybe you need to do actions because it could be quite costly because it's so frequent. If the severity is 10, then basically if these are 0, then maybe you don't need to do anything. But if these are even slightly above, especially this one, above 0, so then typically you need to do something. So the severity, of course, is something that if that happens, even it is very, very rare, then you might be get the lawsuit for that. You may need to pay huge compensations if somebody gets injured or dies because of that problem. Okay, and then there are few typical corrective actions, and there is yes or no in this table, meaning that if you do a redesign of the product, then you can affect on the occurrence, you can affect on the severity, you can affect on the detection. If you change the material of the part, so let's say you take a more stronger material or material which has higher fatigue resistance or whatever, then it changes the occurrence, but of course it does not change the severity of the mode. And most probably it most probably either or. So it can affect on the detection, but also possibility that this is no. So let's say that you change the material to completely new one, then it might be visually different. You might see the problem in a different way, or you might in your testing processes, you might see the different defects in that new material more easily. But it might be that the new material has only minor kind of, let's say, physical or chemical difference. Let's say you are changing from one aluminum alloy to other aluminum alloy, then you can, let's say, increase the mechanical performance, but from the detection point of view, let's say you are checking the, let's say, welding voids with X-ray, so there's no difference. Then this would be no. This is also, of course, looking, let's say, has a little bit also political view. So here in the end, it says that improvement of your statistical process control program or improving the quality plan does not affect on anything. Maybe this is not that kind of strict, because if you are improving the, let's say, statistical process control, then you get data on the defects, you can narrow down the variation of your process and so on. So you could, for example, decrease the occurrence levels. But this table wants to highlight that if you are doing this kind of a statistical process controlling, they are not improving anything from the FMEA viewpoint. Okay, so now what you have basically the RPNs from each and individual failure mode, and then you assign basically some kind of a threshold limit. So basically you think, okay, these are things which I need to correct, and these I can leave as they are. And then you have different types of corrective actions, and then you go forward with that one. So how you basically pick up those modes which you start working on. There could be, for example, this kind of an approach that first you check the highest severity ratings. So you first go through all those failure modes which have severity ranking either 9 or 10. And you work on those. Only you can leave them out, as I said, if the detection and occurrence, they are ones. So basically this is very, very risky problem, but you will never face it. Then you can forget it. But otherwise, you at least consider that is there something which we can minimize the severity of these problems. And then you do the other ranking based on the highest, start from the highest RPNs. And you can just use the ranking so that you put the parts in the increasing or decreasing order. And for that, there are some tools. And one tool is the Pareto diagram, which now let's see if this link works. So this is a link to PowerPoint slide. So what about now? Can you see a Pareto diagram of a coffee maker?
Yes.
Okay, good. So the Pareto diagram is just a way of presenting the order of something. So here, this is, as I said, coffee maker, and now there's only 5 failure modes: pump fails, calcium deposits, electrical failure, clock failure, and heating element failure. And now all these 5 modes, they have their RPNs. So the pump fails, it has something like 300. Then calcium deposits, this is closer to 400, 300 and something. Also this one, this is something like 250 maybe, and this is let's say 200 or whatever. So now you can think that okay, let's work on these 2 and leave these. And then there's always, or quite often, there's also this cumulative curve. So just summing up these. And maybe this is not the best example. Maybe we go to the next one, which is here. So this is more typical, so a little bit more. Here we have a Pareto diagram for an integrated circuit. So this could be, for example, your memory component. And then now here, these modes are from the front end and back end processing. So these are things which can happen during the manufacturing of the component in the wafer level. So here, the first is contamination. Second is the oxide defect, meaning that you have insulating. If it's a transistor, then the gate oxide has some defect. Something else. So this is more the other failures. 3, 4 is corrosion, meaning that you have some processes which cause electrochemical problems. 5 is metallization problem, so your sputtering or evaporation or whatever is not in control. You have your doping of the actual silicon, your N++ areas or whatever, and then there's silicon defect, so let's say dislocations coming from the ingot manufacturing or whatever. So here we have the different modes, and then you see that, okay, the contamination has the highest RPN. Now this is percentage value, it could be as well RPN value, and there is the cumulative value. And quite often, if you have, let's say, more than 5 of these modes, then you have this 80-20 rule, meaning that 20% of the failures are responsible of 80% of the effects of the failures. Meaning that now we are almost there at 80% of the cumulative if we just fix these 2. Meaning the point is just that, okay, let's focus on the most severe ones, and then we can have the highest effect in the as an outcome. One more, this is from printed circuit board. It's just that which kind of components typically cause the problems in printed circuit board. So relays here, they have the highest number, so this is now quantity. So 5 resistors, 4 no failure found, this typical one, 2 cold solder, software bug, operation amplifier or whatever. So these are just arbitrary examples of the Pareto chart. So just put the modes in an order, let's say decreasing order, have the numbers there, and then you have the cumulative values, and then it's easier to really see that, okay, no corrective actions for these because the effect is very small, corrective actions ongoing and corrective actions completed. So then the manufacturer decided that, okay, these 3 we are working on, these 3 we can leave as they are. So that was just the point for having this Pareto diagram. It's easy to visualize that, okay, these things we are working on, and then these things we forget. Okay, then a few more comments. So how to organize the problem-solving process, meaning that how you dig out the improvement. So you start again from the what can affect. Is it the material with effect on this problem? Is it the user who affects on this problem? Is it the testing which affects on this problem? Is it the manufacturing process which makes this problem more frequent or less frequent? And that is, of course, the starting point of your corrective actions. One specific point is that increasing the detectability can be quite easy, but quite often it is not recommended because you are not kind of solving the actual problem. What this means is that you can always add new testing tools. You purchase a new X-ray machine so you can look through the product and see hidden defects. That's nice, but you are not decreasing the effect of or decreasing the number of those problems. So what you end up, you just need to scrap more of your devices so that they are not entering to the customer, but it's not improving the situation at all. I would say that in your assignment, you can also please use the detectability. No worries about that, but this is a little bit more generic comment that detectability is more affecting on the frequency what the customer sees, but it's not basically improving the actual reliability or quality of the product. Then there's another rule of thumb which is also does not need to be valid in your Okay, so typically it is expected that after you have done the first round of corrective actions, then your total RPN should be 50% smaller than the original RPN. But that's not any kind of an absolute requirement for this assignment. Okay, so now we have kind of gone through the process of FMEA in general level, and now I would like to give you the instructions what really the first assignment is. It contains much of the same aspects as what we already have covered. So let's see. Now I will end slideshow. Okay, and then I will try to share my instruction document. Let's see. Just a second, I cannot see now my Word. Strange. Okay, then I need to, sorry, I share this second screen. So hopefully now you see the Word document.
Yes.
Okay, good. So now, first of all, you can do this first assignment either alone or in groups. And it is really, really highly recommended that don't do this work alone. But I will allow that because I know that some of you might be abroad, which then of course the group working is not that easy. Some of you might work during the studies, then it's not that easy to, let's say, agree on the meeting schedules and so on. But I would say that it's much easier to do it in a group, because then you have, let's say, more opinions on how you select the numbers. Typically, when you are doing it alone, you are always stuck into the numbers. So shall I take 4 or 5? Shall I take 4 or 6? But when you are doing it in a group, then it's much easier. And then also you can, let's say, do it a little bit more thoroughly when you do it in the group. And you can kind of distribute the action so that you can utilize your personal competencies better. I put here 2 to 3 persons, because that is typically nice group size for this kind of thing. If you want, you can also have larger group, but then please, let's say, contact me and ask permission, kind of. Just explain that what you are doing and why you want to have a larger group. Because what I'm only afraid is that either you take too complex products, or then you don't have kind of reasonable failure modes for every student to work on. So that's the only thing, that please keep me informed if you want to have a larger group than 3. But really, I would recommend that please do it in a 2 or 3 person groups. That will be much easier for you. You will end up getting better grades, and everything will be much nicer. First of all, you need to select a product, and this is completely up to you to decide. You can use, I would really strongly again recommend that do the FMEA from some product you already know. It might be something which is in your hobby. It might be something which you are working on currently. It might be something what you are doing, some other project in some other course. So that's definitely not prohibited to use the knowledge from the other courses. Only thing is that you should have some kind of an understanding on that product in order to really know at least the basics, how it's manufactured, what kind of components it has, how people are using it, and so on. I'm coming back to that later on, but also it would be nice if it contains some electronics. It could be just a mechanical thing, and you can even do with a very simple mechanical thing. Maybe this is a little bit too simple, but not that much. The problem is that in order to assign the severity rating, the product should have some kind of a safety related things. And for this kind of a pen, for me, it's a little bit difficult to consider how one can affect on the safety of this. Of course, I can stick it in my eye, but maybe that's my problem, not the problem of the manufacturer of the pen. So now I have listed here quite a lot of different types of products, which you can pick one here, or you can pick your own. So these are from household, these are from fancy electrical gadgets, whatever, smart shoes. It could be something to do with the medical electronics, like implantable pressure sensor or glucose sensors for heart beating or sugar levels. It could be diving watch. It could be something which you use for transporting yourself. So it could be standard bicycle or motorbike or hoverboard or whatever. Or it could be let's say smaller part of a larger system. So it could be, for example, LiDAR, so radar, which is using laser light. It could be a tire pressure sensor. So, for example, from automotive, there are quite a lot of examples. So, whatever, and if you want, just you can also ask me. I mean, to propose something and ask my opinion with if this is good or not, and then I try to give my advices. But anyway, the kind of topic in that sense is completely free. So what you do is as I just presented the whole FMEA process. First, you start reviewing your product, and maybe I would say that if you cannot figure anything else, then you can take the bike. The bike is in that sense quite nice that we all know how it works. We know all what are the parts, but so far I have, let's say, read through at least 100 FMEAs from bike, so I'm not that interested in that anymore. But it's a very good option if you cannot figure out anything else. Then that's quite simple. I would say that the complexity of the product is in reasonable level, and it also, of course, has quite obvious safety related things like steering, like braking, and so on. Now, concerning the product, whatever it is, you don't need to analyze all parts. You just need to analyze certain number of parts. So I have here also tried to emphasize that it is better to form a group rather than do it alone. If you do the work alone, you need to include at least 10 parts and analyze at least 20 failure modes or mechanisms from them. If you are doing the crop in a 2 or 3 person group, then you take minimum of 20 parts and you analyze 30 failure modes or mechanisms. So here is just a clarification that what is the difference between failure mode and failure mechanisms. So fracture is a failure mode and fatigue fracture is a failure mechanism. So the mechanism is the reason behind that mode. And as I said, this is quite often, even in the literature, mixed up. And here it really does not have too much effect if you are talking about failure modes or mechanisms, as long as you yourself understand that when you are affecting on something, you are making the changes, you are chasing the failure mechanisms. And then you have the failure mode, which causes the problem. Is it 30 modes or mechanisms each or in total? In total. So this is for the whole group. And then you need to, I'm coming back to this in a minute. So what you need to do personally. I will answer on the other question later on. So what my point is that try to select different kinds of parts. So for example, here you can select small parts, large parts, parts which are critical from safety point of view, parts which are not critical, and so it's easier for you to make the decision that okay, this is a part which I will have my corrective actions, and this is the part which I don't do anything. So for example, you have your pedals, you have the rims, you have your seat, you have your cat's eye, and so on. So assigning the severity and making the corrective actions is completely different which part you take. So it's easier for you if you kind of have larger distribution. So then it's more obvious that, okay, let's pick these and work on these and forget these. And then you do all these things. So this is what I've already went through. So brainstorm the potential failure modes, you assign the numbers. So these are all the same which we already went through. You calculate the RPN by multiplying the severity, occurrence, detection. You calculate the total number. Then you prioritize the failures. So you do the Pareto diagram. You first work on the highest severity ratings. Then you define the critical RPN, meaning that, okay, these are the failures we need to work on, and these are what we can forget. So you need to have this, let's say, 30 modes, and then here you define that, okay, let's work on these 10 or whatever. Blah, blah, blah. This is something that we have already gone through. So after you have done your corrective actions, then you calculate the RPN. Again, you should be below 50% of the original one, but this is not a requirement, absolute requirement in the assignment. And then the important things. Sorry, I'm again spending too much time, but we still have 2 more minutes, I think. So what is the grading? Because this is important, of course, for you from your point. So you need to have for one group. If you do alone, of course, then you do it alone. But if you do it in a group, then you have a short introduction of the product. So you need to tell me what is the product, how it's used, what kind of parts it's made of, how it's operated, and so on. And that is maximum of 3 points. And it's 1 per group. So all group members will get, you can use the same description and you will all get the same points. Then you need to fill the FMEA worksheet. There's an Excel sheet available, or you can use whatever Excel FMEA sheet you find from the internet. So that is just to list all the numbers, all the failure mechanisms, and so on. Then you do the Pareto diagram before the corrective actions and after the corrective actions. So all these are 1 per group. So you can have same, you can use the same worksheet, you can use the same Pareto diagrams. You just do it, and then you get the same number of points. And then the individual part. If you do this in a group, so each of you need to have 3 to 5 failure modes or mechanisms where you really in detail describe the problem and the corrective actions. And that is up to 6 points. So this is half of the points are given to the whole group and half of the points are given individually. And now how many points you get is dependent on the depth of your analysis. So here are some examples. So if you just say that, okay, let's pick a stronger material because this is too weak, let's change the aluminum to steel, then you get 1 point. You have a solution, but you have not justified it at all. In order to get 3 points, so half of out of the 6, you build a, let's say, nice engineering story behind, but you don't need to look at it from every practical viewpoint. So based on you think that you have something which is too weak mechanically, then you check that, okay, let's change the aluminum alloy to titanium alloy, and then you a little bit discuss that, okay, what does it mean from the processing point of view to have titanium alloy instead of an aluminum alloy? How would it affect on the cost, and so on? So an engineering story, but not completely realistic. So for example, you don't need to consider that, okay, all the different types of titanium alloys and how they could be welded and so on. If you want to get the full 6 points, you need to try to be realistic. So for example, from the cost point of view, maybe the titanium alloy is out of let's say practical possibilities. So you need to go on some different aluminum alloys. You go to the literature, you search for aluminum alloys which have different alloying elements, like instead of the cheap aluminum zinc alloy, you go to some aluminum magnesium, these alloys which are used in aeroplanes or whatever, and you can improve the mechanical properties, but you don't kind of drastically increase the cost. So this then if you go through all, not all, but several different aluminum alloys, their different types of properties, how they would withstand on different use conditions, and based on that you justify your selection, then you get the full points. Okay, so there's a discussion ongoing, and instructions are already in my courses, yes, and there were some problems with the videos. Okay, that's not now. I will. Okay, so what else? Deadline is here, and now, sorry again, a little bit overtime. Any questions? Any other comments? I will let's see. If, okay, you can see the instructions. Would there be any options for selecting a group in my courses? Yeah, good question. So you can please use the discussion forum. So you can put there in the general part, you can put there that, okay, I would like to do FMEA in group for this kind of a topic. Would you like to join? And then you can kind of agree on that. That's one way. What else? Of course, you can use whatever ways to form the group, but from the course point of view, I think that's the my courses page would be the best way to find a group and a topic. And if it turns out that, okay, you will have too many students for one topic, then you can just split it to 2. So if you have 6 interested students, then just 3 and 3. You can have the same topic. It doesn't matter. So no worries about that. Okay, so concerning the instructions, so I think someone checked, and the file is there, the instructions are there, and the submission box should be open. Okay, it's in 4 weeks, not needed now. Anything else? There was one raised. Was there still someone who raised hand?
Yes. I have actually 2 questions about the blueprint. Do we do them from scratch, or do we get them from open source?
Sorry?
for the blueprint, like the engineering drawing and those kind of things, like do we have to make them from scratch, or do we get them like from open source, from like data sheets?
It's of course completely dependent on what you select. So of course I don't have the blueprints for each and every device in the world, but just think about because what I wanted to emphasize is please try to pick a product which you already know you are interested in, so it's easier for you to really go inside. Let's say that sometimes people have in this course have, for example, taken some of their own old products which they tear down. They have some old, let's say, camera or whatever, and then they just decide, okay, I'm not using this anymore, so I can tear it down and break it into pieces and check what there is. Or you just try to Google the contents, because there's at least for this kind of smart devices like diving watches or smart watches or phones, these reverse engineering reports you can find quite easily without any cost.
Right, and about the failure mode for the individuals, like so it's in the same device, of course, but mainly like before we make some steps, we will go through the failure modes already, right? So we, in this part, like maybe we can divide them like between us, and then we can include them in the general report of the group.
Yes. So the idea is that first in a group you think together, decide the product, you brainstorm together the failure modes and mechanisms, and then you split the work so that, okay, you decide that, okay, Mustafa, you will take this component and the failure mechanism related to that one, and then you peers they work on something else, and then you have kind of in the report you have the joint part, so you have the generic description of the product, you have the FMEA Excel, and then that is same for everyone, and I'm grading that same points for everyone, and then you have your individual part. So then you just need to tell me that, okay, now I was working on these and these, and this is my contribution to the work. And then I will grade that one individually, because I don't want to give only a group grade. I want to have, if somebody wants to put more effort on kind of doing the corrective actions, then I want to allocate more points also. And if there's someone who is just happy with the 6 points from the joint common part, then you just try it in your own part that, okay, let's change the material because it's stronger, and that's it. Then you get only one point of that instead of 6.
Thank you so much.
I know that this is first, this is quite, let's say, might be a little bit confusing. There are so many parts here, but start working on it immediately. Then when you have these questions, you can use these lectures after the lectures, or you can write your questions into the discussion forum. I will open the discussion now today. They're just writing that please put your questions here and something like that. So you can ask the question there, because then most probably all the other groups are wondering the same stuff, which I kind of forgot to inform. Anything else? Maybe I will at least